Let's do a numeric problem based on the velocity of approach, and that way your understanding would be more clear on this concept. Ball A moves with a uniform velocity of 10 meters per second along a tabletop at an angle of 30 degrees with the horizontal as shown. Simultaneously, ball B moves with a uniform velocity of 12 meters per second at an angle of 60 degrees with the horizontal. While ball A is projected towards the right, ball B is projected towards the left. We have to find the velocity of approach when they have just started moving, because remember, the velocity of approach will change with time. And we will use the same steps that we had laid out in the previous lesson, but with one small change. In the previous lesson, we spoke about obtaining the relative velocity as the first step, and in the second step, we take the components along the line joining A and B. In this problem, let's do step 2 first and then step 1. And you will see that it will not make a difference in the final outcome. Let's just first concentrate on ball A. As a first step, we find its velocity component along the line joining A and B, and we ignore the component that is perpendicular to the line joining A and B. So we haven't computed the relative velocity as the first step. We have simply taken the velocity component of A along the line joining A and B, which is VAX. So VAX is VA cos 30i or 10 cos of 30i. Now let's do the same for B. And like we had done for A, we take the velocity vector B and resolve it into its components. We ignore the component perpendicular to the line AB and we consider only the component along line AB. Although the angle of 60 degrees is shown here, VB is a vector making an angle of 120 degrees with the horizontal x-axis in an anti-clockwise direction. In vector terms, we can write VBX as 12 cos of 120i or minus 12 sine of 30i, which is negative, since this component points in the negative direction of the x-axis. Now we have both the velocity of A along the line AB and the velocity of B along the line AB. And in this problem, we have interchanged steps 1 and 2. Now in step 1, we obtained the components of the velocities along the line AB. Now, as a next step, let's obtain the relative velocity of these components along the line AB. The velocity of approach or separation is the component of the relative velocity along the line AB. So in this case, we have VAX and VBX, and by definition, the velocity of approach or separation will be the difference between VAX and VBX. Be careful with the signs here. VBX is itself negative, and minus VAX will be negative too. The velocity of approach of VB with respect to A being negative means that if we were watching this from A's frame of reference, we would like to see B approaching A along the negative direction of the x-axis with a speed of 12 sine 30 plus 10 cos of 30. It is clear from the diagram that both these components will cause A and B to approach each other. So we term this as the velocity of approach. Suppose we look at it the other way. The velocity of approach of A with respect to B is Vax minus Vbx. Now this is positive since Vbx is minus 12 sine 30. This would mean that if we were in the frame of reference of B, then we would see A approaching us in the positive direction of the x-axis with a speed of 12 sine 30 plus 10 cos of 30. So you can see that the magnitude of approach remains the same whether it is A to B or B to A, only the sign changes. And in both cases, whether viewed through the frame of reference of A or the frame of reference of B, A and B approach each other, and therefore we will term this velocity as the velocity of approach. Also important to understand is that this is the velocity of approach at that instant. At every instant, since A and B move, the line joining A and B will keep changing. So what we have computed is based on the snapshot that we have taken when A and B were in their starting location. For the velocity of approach or separation, we could also begin by taking components of the velocities of both bodies along the line joining the two bodies. Then we could take the relative velocity of these components along the line joining the two bodies.